Good day, I'm Norman Wildberger. Today we're moving towards establishing multisets as a really flexible and powerful tool to organize mathematical structures, but also to set the stage for abstract algebra. So it will turn out that this notion of multisets is actually very, very flexible and fundamental, allows us to organize systematically a lot of interesting topics, such as group theory, ring theory, field theory, and other things. So multisets are, in fact, arguably much more flexible and powerful notion than set theory. Set theory is perhaps to be thought of as a special case of multiset theory. Still interesting, but really part of a bigger picture. So today what we're going to do is we're going to take the concepts that we introduced from the natural numbers last time. We talked about the natural numbers as forming a realm, where we have these three operations: addition, union, and intersection, just considered as operations on the natural numbers. Actually, natural numbers extended with 0. So the union of two natural numbers was just the max, and the intersection of two natural numbers was just the min. And we saw that we had all kinds of nice properties in terms of the interaction between these three operations. So today we're going to observe that that structure translates almost verbatim to this much larger situation of multisets. We're considering M set nk, k M sets from n. N is a natural number. One of these k M sets is, well, an M set which has k elements. Each one of the elements is a natural number between 1 and n. So n is fixed, k is fixed. Then we have a precise meaning of what a km set is from n. In this video we want to extend this a little bit. So we're going to consider the realm M set n, now only depending on the single number n. So we're considering here M sets which are built from the numbers 1 through n. Those are always the ingredients. But the sizes of these M sets is variable. It's not fixed to be a certain k. We're allowing different k's together in the same story. And we'll see that it's this situation that allows us to extend these three operations from the natural numbers into this setting here. And we'll see that we get our realm, M set n, which extends naturally the realm of natural numbers. So, very interesting, powerful, flexible kind of arrangement here. But still very precise. We're still talking about mathematical objects about which we can all agree completely. Okay? All the entries have to be numbers from 1 to n. N has to be fixed. And we're specifying that in each and every case, the natural numbers that appear have to be in Hindu-Arabic form. No alternate descriptions are allowed. So we know precisely what we're talking about, and everybody can agree whether a given object is in here or not in here. So the essence of mathematics, as I want to emphasize, right, that we all know exactly what we are talking about. So one of the features of this development is that we're allowing ourselves to extend our notions. So once we've agreed on a certain kind of mathematical object, we are allowed to later on extend it, make it bigger, increase the size of the arena in which we're working. That's what we're doing here now. We're considering multisets from n, where there's no longer a specific k dependence. We're allowing the k to be variable. So suppose n is a natural number, 1, 2, 3, 4, 5, etc. A multiset from n, what does that mean? It is a km set from n for some k in natural numbers plus. And this type is M set n. So for example, M set 5. It's a new type of mathematical object which consists of all the k M sets from 5 that we can think about, that we can write down. Here is one where k is 4. Here's one where k is 3, k is 0, k is, well, whatever it is, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay? So these are all examples of multisets from 5, because all of the actual entries are one of 1, 2, 3, 4, or 5. So all the elements are from this collection, and if M is an M set of 5 and L is a natural number, then where L is one of these numbers from 1 to 5, then this is how we will denote the multiplicity of L and M. So little m sub capital M of L, the multiplicity of L in M. So this is counting how many times the number L appears as an element in our M set capital M. Right, so the multiplicity is always a natural number or possibly 0. And this is a very important number associated to this L. So we're counting the number of times a given element from 1 to 5 occurs. So the multiset is really determined by knowing how many times the 1 occurs, how many times the 2 occurs, how many times the 3 occurs, how many times the 4 occurs, how many times the 5 occurs. If we know those 5 multiplicities, then we know the multiset in M set 5. And it's these multiplicities that really give us the link between this M set theory and the realm of natural numbers that we talked about in our last video. Right, so just to make sure that we understand our notation, here's a few examples. So here is a M set capital A, which is consisting of 1, 2, 1, and 3. Here is B, which consists of 5, 5, 5. C, which is the empty M set. And D, which is 3, 3, 3, 1, 1, 2, 4, 5, 4, 4, 5, 1, 1, 3, 2. And let me remind you that we're talking about multisets, so the order here is unimportant because there are no commas. There's only spaces separating the elements. That's our convention for the data structure being unordered. It's a multiset, and repetitions are allowed. That's represented by the fact that we have square brackets. So these are all in M set 5 because all of the actual elements that appear are from 1 to 5. Okay, so the multiplicity of 1 in A is 2. The multiplicity of 2 in A is 1, appears once. The multiplicity of 3 in A is 1. The multiplicity of 4 in A is 0. The multiplicity of 1 in B is 0. The multiplicity of 5 in B is 3. The multiplicity of 7 in C is 0. Okay, 7 is actually not a possible element of M set 5. But we could probably safely say that the multiplicity of this 7 is still 0. It doesn't occur. And the multiplicity of 5 in D is 2 because there's 2 of them right there. So clearly if capital M is a M set from 5, then the multiplicity of any L in M is 0 if L is bigger than 5. All the elements have to be in the range 1 through 5. So if we ask for the multiplicity of 6, 7, 8, or 3,000, it will necessarily be 0 if our capital M is an M set from 5. Okay, so here is another M set E, an M set from 5. The multiplicity of 1 in E is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, yes. And the multiplicity of 2 in E is 5. 1, 2, 3, 4, 5. So the multiplicity can be very large. Okay? There's no real bound on the multiplicity that we're talking about here. We are allowing K multisets, even for very large K. Although the 5 is fixed, the size of the multisets that we're talking about is not fixed. Can be very large, even if this n is actually small. All right, so I hope that what I'm doing here is kind of obvious, that you'll think, this is so elementary, you're just making up kind of pretty reasonable natural definitions that are easy to understand. So I hope you have that point of view. But still, it's important to establish our notation so we know precisely what we're talking about. And it will turn out that this algebra of multisets turns out to be considerably more interesting and useful than maybe it appears at first glance. Okay, so now things heat up a little bit because we introduce the operations in M set of n. So suppose that capital A and B are M sets from n for some fixed n, a natural number. Right, so we are now going to define A plus B, A union B, and A intersect B, which also belong to M set of n. So we choose two things that are of this type, then these operations give us another object also of the same type. Right, so how are we going to define these operations? We're going to define them in perhaps a somewhat novel way. We're just going to define them in terms of the multiplicities of elements. So have a good look at these definitions. So we're going to define A plus B to be the multiset such that the multiplicity of L in A plus B is the sum of the multiplicities of L in A and in B. What does this mean? Well, it means that if L is a natural number, that the number of times L appears in A plus B is exactly the sum of the number of times it appears in A and the number of times it appears in B. Now, since A and B are actually in M set of n, we could have said that we're just restricting ourselves to L's from the range 1 through n. And exactly in a similar fashion, we define the union A union B by the condition that the multiplicity of L in A union B is the union of the multiplicities of L in A and in B. And I remind you that union at the level of natural numbers is maximum. So we're seeing how many times L appears in A and B and taking the maximum of that, and that's the number of times that L appears in the union. That's for L in natural number, but in fact we only need to check from 1 to n. And intersection, similarly, the multiplicity of L in A intersect B is the intersection of the multiplicity of L in A and the multiplicity of L in B, which is the minimum of the numbers of times that L appears in A and appears in B. So we need actually only check L's from 1 through n because everything here is in M set of n. In particular, it's a completely finite procedure to compute specifically the sum, the union, and the intersection of any two given M sets from n. Notice this is a very efficient kind of way of defining what these things are. It's maybe more precise than what you're used to when we define union of sets. How does one define the union of sets? Well, we haven't really talked about that yet because we haven't talked about set theory. But if you think about how you define unions of sets from naive set theory, it's a little bit vague, I think. Okay? Here we're being very precise. We know exactly a range of values. We know exactly what it is that we're computing. We can check mechanically and convincingly, completely, whether we've actually taken the union or an intersection or a sum. And crucially, what distinguishes this from ordinary set theory is the possibility of taking the sum of two M sets. Right? That's something you cannot do in ordinary set theory. That's what makes this thing actually considerably more interesting in some levels than set theory. Okay, so an example. Let's work in M set of 3. So here's A, which is an element of M set 3, so it's a multiset from 3, because all the elements are 1s, 2s, and 3s, and not any other things. Here, this B is also an M set from 3. So what is A plus B? Well, that's the sum. So we have to sum multiplicities. So the element 1 occurs 4 times here and 1 time here, so we have to put 5 of them in the sum. Element 2 occurs once here and 3 here, so we have to put 4 of them in the sum. Element 3 occurs once here and 0 times here, so we have to put 1, 3 in the sum. How about the union? Union corresponds to maximum of multiplicities. So 1 occurs 4 times here, once here. The maximum of those two numbers is 4. So in the union, 1 will occur 4 times. 2 occurs once here and 3 times here. The maximum of 1 and 3 is 3. So 2 occurs 3 times. 3 occurs once here, 0 times here. The max between 1 and 0 is 1. So the 3 occurs once. And what about the intersection A intersect B? Well, there we have to take minimums of multiplicities. So 1 occurs 4 times here, once here. The minimum of that is 1. So there's 1, 1. 2 occurs once here and 3 times here. The minimum of that is 1. So there's 1, 2. And 3 occurs once here and 0 times there. The minimum of that is 0. And so 3 occurs 0 times there. So it's very concrete and methodical. So what we're really doing is we're just considering each element 1, 2, 3 separately. Make a calculation for the element 1, calculation for the element 2, calculation for the element 3, and sort of keeping them all separate. And so we may now check that each of the laws established for the realm nat plus holds here also for M set of n. The fact that essentially these 3 operations are done 1 element at a time means that the various rules that we've established for the realm nat plus will almost automatically hold for this larger situation where we're considering M sets from 3, or M sets from 5, or M sets from n. Alright, so we have this theorem. Suppose that we have k, m, and n, which are M sets from some n. N is a fixed natural number. Then, the various operations, addition, union, intersection, that are operating here in this realm of M sets from n, obey the following laws. And these will be very familiar. In fact, they're exactly the same laws that we've already seen in the context of natural numbers. But now we have capitals because we're talking about M sets rather than individual natural numbers. But that's pretty well the only difference. So commutative laws, M plus n equals n plus m, M union n equals n union m, M intersect n equals n intersect m. Associative laws, k plus m plus n equals k plus m plus n. Similarly for the unions, similarly for the intersections. The distributive laws, of which these are sort of the novel ones because they combine addition and union and intersection in somewhat novel ways. So k plus m union n is k plus m union k plus n. And k plus m intersect n equals k plus m intersect k plus n. And these ones are the same thing, just with the order changed. And here are the more familiar distributive laws with just unions and intersections. So k union m intersect n equals k union m intersect k union n. And interchanging unions and intersections, k intersect m union n equals k intersect m union k intersect n. And here are the same laws, sort of with the orders swapped. Okay, but there are some more laws. All right. So there's identity laws. And here the M set which plays the role of 0 is the empty M set, which has nothing in it. So the multiplicity of any of the L's is always 0. So empty set plus M equals M plus empty set equals M. empty set union M equals M union empty set equals M, and empty set intersect M equals M intersect empty set equals empty set. Idempotent laws, M union M is always M, M intersect M equals M. The absorption laws, that M union M intersect N equals M, and M intersect M union N equals M. Cancellation law, that if K plus N equals M plus N, then we can cancel the N's and deduce that K equals M. And our summation law that connects all three operations, that M union N plus M intersect N is the same as M plus N. So nothing novel at all here, really. We're just copying the realm laws for natural numbers and asserting that the same laws, exactly the same laws, hold for M sets from N. We fix an N like N equals 5, then the M sets from N form a realm where exactly the same laws are holding. All right, what about the proofs of all these laws? So this is something I want you to give some thought to. Okay, so I claim that actually the situation is dramatically simple. That each of these laws is an assertion about how many times a number L, a natural number, actually with L between 1 and N, occurs in the various M sets. If one M set equals another M set, it means that the multiplicities of any L in this range are equal. That's what it means for them to be equal. So each of these laws reduce to the corresponding realm laws for the natural numbers. If we restrict our attention to just a specific L in this range, then the various assertions just reduce to the corresponding assertions for natural numbers. So let's illustrate, for example, one of the laws. Suppose that N is 5, so we're talking about M sets from 5. Here are a couple of M sets from 5. K, 1, 1, 2, 5. M, which is 2, 2, 3, 5. And N, which is 1, 2, 4, 4, 5. Then how about K plus M union N? Well, there is K. Forming the union of M and N means that we have to go through and take the maximum multiplicities. So 1 occurs once here, that's the max. 2 occurs twice here, that's the max. 3 occurs once here, that's the max. 4 occurs twice here, that's the max. And 5 occurs once. So there's the union of M and N. And when we add them, we just put everything together. So the 1s occur a total of 3 times. The 2s occur a total of 3 times. There's a 1, 3 in total. There's a couple of 4s in total, and altogether a couple of 5s in total. On the other hand, the distributive law that corresponds to this is that this should be equal to K plus M union K plus N. So let's see if that's true. K plus M, just what you get when you plop these together. 1, 1, 2, 2, 2, 5, 3, 5. And K plus N, put these two together, 1, 1, 2, 5, and 1, 2, 4, 4, 5. And the union here. So again, we have to go through each element and find the maximum multiplicities. 1 occurs twice here and 3 times here, so there's the union, 3 of them. 2 occurs 3 times here and twice here. The max is 3, so there's 3 2s in the union. 3 occurs once here and 0 times there, so there's a single 3 in the union. 4 occurs 0 times here and twice here, so there's 2 in the union. 5 occurs twice here and twice here. The max of that is 2, so there's 2 5s. And then, with any luck, we'd check that, yes, these two sets are indeed equal, and we verified one of the distributive laws in this particular case. I'd like to point out that, so this is also proving for us in the special case when we're talking about sets, which we're still to define, but I just want to point out Now we're also proving the distributive laws for union and intersections at the level of sets as well here. Okay, so this argument includes that, and it's a multiplicity kind of argument which one often doesn't employ in set theory because the multiplicity seems to be too boring. It's either 0 or 1 all the time. It's actually a kind of a useful way of thinking about this algebra. All right, so please give some thought to this proof. Have a look through the various laws. Convince yourself that they really do reduce to the laws for the natural numbers. And if I've made a mistake, point it out, please. We'll correct ourselves. Okay, so I want to point out that we can apply a few of the other ideas from the natural number situation to this much more general multiset situation. In particular, the idea of sub-multisets and the idea of circle subtractions, which occurred in that situation, can be immediately translated over. Again, just by framing all the definitions in terms of multiplicities of single numbers one at a time. So if m and n are multisets from fixed n, we can define this ordering that m is less than or equal to n. Okay, we can actually use this terminology. M is less than or equal to n to mean that the multiplicity of a given L in our standard range in M is less than or equal to the multiplicity of L in N. So for each one of these L's from 1 to N. So we can introduce this notation for sub-multiset now. So making the correspondence between multisets and natural numbers very tight, so a complete parallel. So we're going to do that, and so this is maybe interesting kind of notation. And then we can check that, just as we had for natural numbers, that m is less than or equal to n. It's really equivalent to the m union n equals n, or equivalently that the m intersect n equals m. And there's also a transitivity that if k is less than or equal to m and m is less than or equal to n, then k is less than or equal to n. And we also introduced circle subtraction. It's a kind of a limited kind of subtraction that keeps us in the realm of natural numbers. So we can do the same kind of thing here. So if m and n are multisets from n, we can define m circle subtract n to be d. So we can define this saying that the multiplicity of L in D is essentially the circle sum of the multiplicities here. In other words, the multiplicity of L in M minus the multiplicity of L in the intersection. And the way we've defined this multiplicity, it's the multiplicity of L in M intersect the multiplicity of L in N. So that's another way of describing this circle subtraction. So we have this kind of partial subtraction in the realm of multi-sets, just as we do in the realm of natural numbers. Okay, so we haven't done anything really profound in terms of mathematical insights here. We've just basically translated our structure from the natural numbers into the situation here of multi-sets from a fixed n. But this is very kind of cool thing to do. And in our next video, we're going to see that there's this nice algebra of multi-sets. And we're going to investigate some additional notation that will give us even more flexibility in terms of understanding, working with, and actually applying these multi-sets. We're going to see that these are very, very useful kind of conceptual tools. We're organizing stuff here, and the kinds of things that we're organizing, the way we're organizing things, is very useful for abstract algebra and other areas of mathematics. We'll see. Okay? So next time, some algebra with multisets. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.